All right, this stream and this recording are to discuss the recitation problems from last week, where we introduced Newton's laws and force diagrams. I'm using a different recording setup in a different room now, so bear with me if there are any glitches. So this is Wednesday's recitation problems from week 4, I believe. So the first problem asked you to envision a person in an elevator car. Oh, that's off the screen. This is what I meant by glitches. Yep, can't see that high. Let's move the elevator down lower. So we have a person in an elevator car. And that elevator, being an elevator, could be accelerating upward. It could be accelerating downward. And the question asks you to envision what forces act on this person, in particular what the normal force on them would be. So ask you to draw force diagrams for all of these situations. So there are 3 scenarios. The first one is the car is moving upward and its speed is increasing at a rate of 1 meter per second squared. So moving upward, rate increasing at 1 meter per second squared. Well, I'll write all of them up here first. The second one, car moving downward, speed increasing at 1 meter per second squared. And then the final one, the car is moving downward and its speed is decreasing. So that's what we changed at 1 meter per second squared. So this is just a reminder about thinking clearly about acceleration. So if we are moving upward and becoming faster, the acceleration is upward. If we're moving downward and becoming faster, the acceleration is downward. But if we're moving downward and the speed is decreasing, like if we're moving downward but coming to a stop, then the acceleration is upward. So if we choose our conventional coordinate system, where that direction is positive and this direction is negative, then the acceleration here is 1 meter per second squared, positive. The acceleration here is minus 1 meter per second squared, because that's down. And here again, the acceleration is 1 meter per second squared. So that's the diagram, that's the cartoon, thinking about the acceleration. Now the remainder of the problem asks us to write the force diagrams for each situation and determine how big all of the forces are. Now remember, forces are physical pushes and pulls. Acceleration is not a force. So I'm going to tilt the camera up. Give me 1 minute. I realize the top of the board is cut off. Acceleration is not a force. Velocity is not a force. Only physical pushes and pulls are forces. So our person is experiencing only 2 forces. They're standing on the bottom of the elevator. So the bottom of the elevator exerts a normal force upward on their feet, and gravity pulls them down. So the force diagrams are actually pretty simple. All all cases are the same, we have a dot representing the person, the normal force from the floor pushes them up, and gravity pulls them down. I'm writing gravity with the symbol mg because I know that's how big it will be. I don't need any subscripts on any of these. Now, why are we doing this problem this way? I know the person's weight. I know the person's mass is 100 kilograms. G is about 10 meters per second squared, so I know that mg is going to be about 1,000 newtons. But the normal force, I do not know. You can't just come here and say, oh, this is a balancing force or something like that, and say, well, the normal force is 1,000 newtons upward. Not always. The normal force, remember, we don't know it yet. So remember our 1, 2, 3 approach to these problems. This, what I have written now, is part 1, drawing force diagrams. It's the same for all of them. Part 2 is to write Newton's law of motion. So this is where this thing that I've used most of my board to write out comes in. I know the sum of the forces equals ma. And in our case, the sum of the forces is just here. The normal force goes up, mg goes down, minus mg equals ma. And, well, the force I don't know is the normal force. So this allows me to solve for the normal force. So I get, doing my algebra, I move mg to the other side. I get F sub n equals ma plus mg. Or, if I want to write it in a different way, I could write this as, I could undistribute the m and write this as m times a plus g. Remember the problem where we put Kiki in the elevator car? And you wound up with the result that it was as though the acceleration of the elevator was in some sense adding to gravity. This is the same result. So now that we know this, now that we know that the normal force, I'm just going to recopy this, that the normal force is m times a plus g, I can calculate the normal force for each of these cases. So here, the top one, the acceleration is 1 meter per second squared. So, I want to use a different color. The normal force is m times a plus g. Mass is 100 kilograms. A is 1 meter per second, G is, there's meter per second squared, G is 10 meters per second squared. So the normal force is 1,100 newtons. Here I'm accelerating downward. So the normal force is m times a plus g. Here a is negative. G is, as it always is, plus 10 meters per second squared. So this gives me a normal force of 900 newtons. And here, the acceleration is again the same positive value as part A. So this gives me a normal force again of 1100 newtons. So this tells me that the floor of the elevator pushes up more on me when I am accelerating upward, whether that's because the the elevator is starting to move up or stopping moving down. But the normal force pushes on my feet less when the elevator is accelerating down. One of your homework problems for this next week is to go to an elevator and experience this and see how this works for yourself. So that's problem 1. Problem 2 is another sort of prototype. In this problem, rather than just dealing with one object moving, or one object that might move, now you have 3. This is kind of our prototype for dealing with more than one object. I'm going to take the board off. I'm going to go retrieve one more color of chalk. Where did I put my box? Here it is. Let's see. This color and this color. So the next problem, I ask you to envision 3 books sitting on a table. So we've got a table. On it, I've got 3 books, which I'm labeling A, B, and C. And the question is simply to think carefully about the forces and figure them all out. Now, I've told you that each book weighs 10 pounds. So we only need one letter M, right? We don't have to say M-A, M-B, M-C, because they're all the same. So M-A-G equals M-B-G equals M-C-G equals 10 pounds. This is probably the only time in our class we will use American units. So we're going to approach this problem in the same way we approach every other problem. Now, this is important. The answer to this problem is obvious. We know the table has to push up on the stack of books with a force of 30 pounds. The reason we're doing this problem is to practice getting an answer that we know is correct using a method that we'll then apply to problems where the answer is not obvious. So we're going to do the same steps that we always do. We're going to begin by drawing force diagrams for all the objects. So let's start. We're going to do it actually from the top down. That's easiest. So for book C, how shall I do this? I'll do it like this. For book C, its weight goes down, and there is a normal force pushing up from book B. Now I'm going to have lots and lots of different normal forces in this problem. So I need to label them with subscripts. Now, there are lots of different subscripts you could use. Some of your TAs may use a different order. Here, when I write this, I mean the force of book B on book C. Or you could say, well, let me write it this way, the force on C from B. It doesn't matter. All that matters is that you're clear about what the notation means. So I'll make a little label here. When I write this, I mean the force on C from B. Any notation is fine as long as it's clear to you. So that's what's going on for book C. Now book B, it also has its own weight going down, but it's touching two other things. Book A pushes up on it and book C pushes down on it. So now I need room for another down arrow, so I'll just do this. I'll just make the dot real big. You can do that. So let's see, I have C pushing down on B. Thinking about my colors here. So C pushes down on B, so using my notation here, I'm going to label this as FBC. Force on B from C. And A pushes up on it. Do this in yellow. FBA. Force on B from A. For book A, I do the same thing. Let's see, I've got its own weight going down. So this, it's got book B sitting on its head. So I have FAB. And then pushing up on it from the table, we'll draw this in white. FTA. Well, FAT. Force on A from the table. And this is the diagram for book A. So I've got all of my force diagrams. The next thing I need to do is write down Newton's laws of motion. So once I have my diagrams, once I have thought carefully about them, writing down Newton's laws of motion is a pretty trivial exercise. Like I said, I'm recording in a new space, and I notice there's a bit of glare on the board. Let's see, does that make it better? Bit. Just gonna try some stuff. Yeah, okay, that's better. It's glare on me. That's okay. The board is what you're here to see, not me. I'm gonna twiddle this a bit. There we go. That's too dark. You know what? We'll go back to that. Sorry folks, new recording setup, new room. There we go. Okay. The second step is always Newton's laws, where we write down the equations that correspond to our diagrams. So we should have three equations because we have three diagrams. We'll just do them one at a time. The sum of the forces on C is MAC. So here we just copy them off. We're going to choose the standard coordinate system where up is positive. You don't have to make that choice, of course, but this is what we'll do here. So I have FCB minus MG equals MAC, well, we know that's 0 because nothing is accelerating here. It's just sitting on the table. Oh, we are too bright. There we go. Now we've got book B. Well, what happens to it? Well, again, I've got 3 arrows. I just read them off my diagram. FBA, so the force on B from A, minus the 2 that go down, minus mg, again equals 0. Because we know the acceleration of everything is 0. And finally, we'll do the same thing for the last one for book A. So sum of forces on A is its mass times its acceleration. So again, just read the forces off the diagram. The force on A from the table minus FAB minus mg equals 0. So here are my equations. And after you write down your equations, it's always a good idea to take stock and look at what you know and what you don't know. How many unknowns do you have? Now, I've written mg in 3 different colors here for the 3 different objects, but we know they're all the same. We know all of the books have the same weight. But notice that I have 5 unknown normal forces. The force on C from B, the force on B from A, the force on B from C, the force on A from the table, and the force on A from B. I needed to write all these subscripts to make sure my notation is clear. But notice these 2 that I've both written in orange, I've done that for a reason. These are equal by Newton's third law. Newton's third law says if B pushes on C with some force, then C must push on B with an equal force in the opposite direction. Notice these appear with opposite signs. This one's positive and that one's negative. The magnitudes are the same. Likewise, this pair is also equal. So, once I think carefully about that, I'm down to 3 unknowns. I don't know the force that the table exerts on A. I don't know the force that A exerts on B. And I don't know the force that B exerts on C. And these 2, of course, are the same by Newton's third law. So now that I understand what's going on, and now that I'm down to 3 equations and 3 unknowns, now it's time to do algebra. So, if I look at this equation, I notice that this is very easy, right? I've got 2 terms on the left-hand side equals 0. So I have FCB minus mg equals 0 tells me right away, if I solve for FCB equals mg. Now, my second equation for B let's see, what do I have? I have FBA. I'm going to change the order of terms here. You'll see why in a minute. Minus FBC equals 0. But notice I've got a formula for FCB. I figured out what that is. So I can substitute that in here. And I get, whoop, that should be FBA. Forgot to write the last letter. So let me just copy this down one more time. I'm going to put mg in for that. So I have FBA minus mg minus another mg equals 0. So that tells me, again, solving for FBA, I get FBA equals 2 mg. Notice that if these two masses were different, then I wouldn't combine them. I would just add together purple and orange weights. And, well, you can see where this is going. For the third one, I have, just going to copy down that equation now. The force on A from the table minus that weight minus FAB, all that's equal to 0. Well, same deal. I substitute in the thing that I just found. That gives me FAT minus mg minus 2 mg equals 0. And that tells me that the force on A from the table is 3 mg. So what did we do? What was the point here? These answers are obvious, right? If I have 3 books that weigh 10 pounds, then this one has to push up on that one with 10 pounds. A has to push up on B with 20 pounds, and the table has to push up on A with 30 pounds. You should have been able to guess that. The reason we wanted to go through this was to show you how the laws of physics will get you the answer you could have guessed without you having to make up stuff. Without you having to say, oh, well, I know that A is going to help hold up C, so let me put in some phantom force FAC. Nope. That doesn't exist, right? Because C does not act on A. No. Should be notated the other way, but yeah, that doesn't exist. The reason this problem is here is to show you that you don't need to make up stuff to get the answers you know are correct. Allow the laws of physics, the Newton's laws here, and then the way algebra works, to solve the problem for you. You don't have to guess what the answer is and put it in by hand. The very last part of the problem asks you to imagine what would have gone wrong if you had messed this up. So suppose you had put in some other force pushing up on C, and you had something, so another mg here. You might wind up with 4 mg, 40 pounds. And some of you may have made that error in your group. And coming down here and getting 4 mg would prompt you to sort of go back up and say, that force isn't really real. So that was recitation from last Wednesday. I'm going to stop the recording now, and then I'm going to start one for Friday.